In 2010, a scientist reached into the Titanic and pulled out something alive. Her name was Henrietta Mann. She was a microbiologist at Dalhousie University in Canada. And what she found growing inside the rusted walls of the world's most famous shipwreck was a living organism, one that had never been described before in science. It was consuming the ship, slowly, methodically, gram by gram. She named it Holomonas titanicae. And here is the thing that should terrify you. This organism, this bacteria, had been eating the Titanic since before your parents were born. Before the internet existed, before the Cold War ended, the Titanic has been alive, in a way no one talks about, for over a century. But that's not even the strangest part, because right now, in the Black Sea, there are ships older than the Roman Empire ships that sank more than 2,400 years ago, and they look almost exactly as they did the day they went under. Joinery intact, hull shapes recognizable, ropes still coiled on the deck. Two ships, thousands of miles apart, thousands of years apart. One being consumed by living organisms, one perfectly preserved. And both of them are telling us the same secret about what the deep ocean actually does to the things we lose inside it. Most people think of the ocean as one place. It isn't. The ocean is layered like a building with floors that have almost nothing in common with each other. At the surface, you have warmth, light, oxygen, and constant motion. Storms churn the water, currents carry nutrients, organisms thrive. This zone, roughly the top 200 meters, destroys things quickly. Wood rots in years. Metal corrodes in decades. Organisms swarm everything organic. A ship that sinks here doesn't last long, but descend past 1,000 meters, and everything begins to change. Temperature drops toward freezing and stabilizes. Light disappears completely. Currents thin to almost nothing. Oxygen levels fall. And the biological communities that exist down here, the ones capable of breaking down a ship, become scarce, specialized, slow. At 3,800 meters, where the Titanic rests, you enter a world that operates on a completely different clock than the one you're used to. A clock where a year on the surface might equal decades of change down here, or nothing at all. This is not a metaphor. This is physics. And it is the reason that what we find down here defies everything we expect. When Robert Ballard's cameras first reached the Titanic in September 1985, the footage shocked the world. Not because of destruction, because of what was still there. A chandelier, still hanging. Bottles of wine, intact. Personal belongings, recognizable. At a depth where pressure exceeds 5,500 pounds per square inch, roughly 375 times the pressure you feel right now, objects that should have been crushed had survived for 73 years. Here is why. Pressure in the deep ocean is not a force that acts like a hammer. It acts like a blanket. When a ship sinks and reaches the seafloor, pressure equalizes around every surface simultaneously. There is no side being pushed harder than another. The ship is not being squeezed from outside, it is being compressed equally from all directions. The violence of pressure happens during the descent when air-filled compartments haven't yet flooded, when the outside pressure exceeds the inside, when weak points fail. That is when hulls buckle, compartments implode, windows shatter. But once a ship settles, the pressure equalizes. And at that point, high pressure may actually slow certain chemical reactions. It suppresses biological activity. It reduces the energy available for corrosion. The crushing depths of the ocean, the depths we fear most, may be among the best preservation environments on the planet. Let that settle. The thing we think destroys shipwrecks might be quietly protecting them. Back to Henrietta Mann, and back to Holomonas titanicae, because this is where the story of shipwreck science gets genuinely strange. What Mann discovered was Not just a bacteria, it was an architect. Halomonas titanicae, along with dozens of other microbial species living in the Titanic's walls, does not simply corrode iron the way rust does. It metabolizes it. It eats it. And as it eats, it builds. The formations you see hanging from the Titanic's hull, those frozen stalactite-like structures that droop from the railings and bow, are called rusticles. They look like metal. They look inorganic, but they are living architecture. Biological structures built from iron byproducts and microbial communities, growing over decades, housing hundreds of interacting species in a miniature ecosystem. Scientists estimate these microbial systems are removing roughly 100 kilograms of iron from the Titanic every year. That sounds like a lot, but the Titanic weighs approximately 46,000 tons. At current rates, the bacteria have consumed less than 1% of the ship. The process is not violent, it is geological. And this is where the real question begins. If this ecosystem is consuming the ship slowly, invisibly, constantly, then what is the ship becoming? Not rust, not rubble, something else entirely. In 2017, a research team aboard the RV Pelagia made a discovery that rewrote what archaeologists believed was possible. At the bottom of the Black Sea, below 2,000 meters of near-anoxic water, they found ancient ships. Not fragments, not impressions in sediment. Ships. A Byzantine trading vessel, an Ottoman vessel, and deepest of all, a Greek trading ship, its construction dating to roughly 400 BC, over 2,400 years old, and it was intact. The hull planking was preserved. The internal framing was visible. Ropes that had been coiled on the deck for more than 2 millennia were still coiled. How? Because the Black Sea below roughly 150 meters contains almost no oxygen. And the organisms that decompose wood, the shipworms, the bacteria, the marine borers that hollow out underwater timber in years cannot survive without it. Remove the oxygen. Remove the biological mechanism. And the process of decay simply stops. This ship sat on the floor of the Black Sea for longer than Christianity has existed, for longer than the Roman Empire rose and fell, for longer than the entire history of the United States multiplied by 12. And when cameras finally reached it, the wood still held its shape. There is no word in normal human language adequate to describe how old that ship is and how preserved it remains. But science has an explanation, and that explanation changes everything we thought we knew about what the ocean keeps. In March 2022, a team of researchers located Ernest Shackleton's ship Endurance in Antarctic waters. The ship had been sinking since 1915, 107 years on the seafloor. When the cameras reached it, researchers described it as being in a remarkable state of preservation. The ship's name was still clearly visible on the stern. Its iconic wooden construction, the same construction that the ice of the Weddell Sea famously crushed, was still structurally recognizable. 107 years at 3,000 meters. And you could still read the name. The reason is temperature. At those depths in Antarctic waters, temperature stays just above freezing around 0 to 2 degrees Celsius year-round. And cold does something remarkable to chemistry. Every chemical reaction has a rate. That rate is governed by temperature. Lower the temperature, and the reaction slows. Lower it further, and it slows more. At near-freezing temperatures, corrosion slows, microbial metabolism slows, biological growth slows. The cold, deep ocean is, in a very real sense, a planetary refrigerator. And some of what it has stored inside has been waiting, frozen in time, for longer than modern humans have been writing history down. Here is the thing that breaks conventional logic. Some of the most modern ships ever built, steel vessels constructed in the 20th century, with advanced metallurgy and industrial precision, have already vanished in coastal waters. Meanwhile, wooden ships, built by hand 2,000 years ago, survive perfectly in the deep Black Sea. Steel is stronger than wood. Modern ships are more durable than ancient ones. So why are the ancient wooden ships winning? Because survival is not about strength. It is about environment. Steel corrodes through an electrochemical process. It requires oxygen, water, and ionic compounds, all of which exist in abundance in shallow coastal environments. Wood decomposes through biological processes. It requires organisms to break it down. Remove those organisms by removing oxygen, and the wood survives indefinitely. The Wasa warship, raised from Stockholm Harbor in 1961, after 333 years on the seafloor, was preserved largely because the low-salinity Baltic Sea had killed off the shipworms that would otherwise have consumed it within decades. Not the deepest ocean, not extreme cold, just the wrong kind of water for the right kind of organism. The wrong environment for the biological mechanism, and the ship survived. This is what deep ocean science keeps teaching us. The factors we assume are powerful material strength, engineering quality, construction age, often matter far less than the conditions around the ship once it sinks. Environment beats engineering. Every time. There is one more preservation force we haven't discussed, and it may be the strangest of all. Burial. When a ship sinks and settles into soft sediment, parts of it begin to sink into the seafloor itself. The lower hull, cargo holds, heavy internal structures, they can settle into silt that slowly covers them. And once buried, everything changes. Sediment blocks oxygen flow. It blocks currents. It creates a physical barrier between the wreck material and the organisms and chemistry of the open water above. Archaeological studies of shipwrecks consistently find the same thing. The most preserved artifacts are always in the deepest sediment. The most intact structural details are always the buried ones. The history that survives longest is the history that disappeared first. The ocean does not preserve things by keeping them visible. It preserves things by hiding them. And the deepest ironies of shipwreck science is this. The parts of these ships we have studied most, the exposed surfaces, the railings, the visible bow, the famous imagery, are the parts deteriorating fastest. What remains of the past is underneath what we can see. Scientists who study the Titanic are often asked one question more than any other. How long does it have left? The honest answer is, we don't know. We have never observed a deep ocean shipwreck through its complete decay timeline. The Titanic is, in some ways, the first wreck we have watched closely enough, across enough time to begin to understand. What we do know is this. The wreck is entering a new phase. Corrosion has weakened critical structural supports. The bow section, the part most recognized worldwide, shows significant deterioration in each expedition compared to the one before. The crow's nest, where lookout Frederick Fleet first spotted the iceberg, has already collapsed. Some projections suggest the exposed superstructure may become unrecognizable within decades. Others believe parts of the hull buried in sediment, shielded from the open water, may persist for centuries. The Titanic will not vanish all at once. It will transition. The exposed parts will collapse. The buried parts will remain. And far beneath the recognizable wreck, at the boundary between steel and sediment, the biological processes will continue long after the last recognizable structure disappears, transforming iron, building new ecosystems, making the ship part of the seafloor itself. We began with a bacteria no one had heard of, eating a ship everyone knows. We found ancient wooden ships that outlasted empires. We discovered that pressure, the force we feared most, may actually protect. We learned that the cold, deep ocean runs on a different clock than anything above it. And we found that the things that survive longest down there are often the things that disappeared from view first. The deep ocean is not a graveyard. It is not a museum. It is something stranger than either. It is a transformation system, one that takes human time and stretches it until it resembles geological time. Ships down there do not decay the way we decay. They transition from engineering to ecosystem, from ecosystem to geology. And some of the ships resting at the bottom of the ocean today may still be there, still changing, still hosting life, still slowly becoming something new. When people hundreds of years from now look back at our era the way we look back at ancient Rome, the question is not whether the ocean will eventually take them. It will. The question is what they become along the way, and what they hold in sediment, in biology, in chemistry that we haven't found yet. Because the deep ocean does not empty the past, it archives it. In the only language the planet has ever spoken, time,